We're going to finish our discussion of the rules of quantum mechanics by turning to Rule 7, the time evolution rule. The textbook describes this roughly as so. So it turns out that any quantum state vector, or ket, can be written as a superposition of energy eigenvectors. So these are eigenvectors, as we discussed, that here have a set eigenvalue of energy. And so if at t equals 0, the quantum state is this, and so this is just some linear superposition of the eigenvectors, where instead of the spin eigenvectors, we're using the energy eigenvectors. If we can express our state like this at time 0, then we can find the time evolved state this way here by multiplying a complex exponential that involves the energy eigenvalue for each one of these states. All right, and multiplying this onto each one of these different pieces here in the superposition. And so again, these are the energy eigenvalues associated with the energy eigenvectors, E1, E2, so on and so forth. Of course, this depends on h bar, which we've talked about, and so this is really important. This is Newton's second law for quantum mechanics, and it's really weird. We're going to spend a lot of time this semester trying to talk about this and justify it, but first we're going to start out just trying to get used to using it. And so here's the steps, the general procedure for time evolution. And these will be the same steps we'll be using pretty much the rest of the semester. So if you're given your initial state, so here's our initial state. So suppose you're given your initial state vector, sort of like this here. All right, so the first step is to determine which eigenvectors are the energy eigenvectors. And so we'll talk about how to do this, but generally in the problem, you can find information to determine which ones are which. Then the second step is to write your state vector in terms of the energy eigenvectors. So we'll also spend a lot of time doing this here. So the first two steps take a little bit of getting used to. And so we'll end up sort of like this here. So if we can express our state as some linear superposition of the energy eigenvectors, then basically the last step is just to multiply by this complex exponential. All right, and again, so these are the energy eigenvectors here, and we're going to multiply this complex exponential with the particular certain value of the energy given. And then once you have this, this is your state vector as a function of time. And so then in each problem, you'll be asked to do different calculations. And so this is the last step. And really that goes along the same lines as we did in the previous lecture as far as calculating different things. So let's now try to do an example. Now this example is very similar to the example they do in the text. So you can get sort of two different views of this. I think ours are slightly different, but it's a very similar thing. And suppose we have an electron that starts out in the positive y state. So its spin is aligned with the positive direction, positive y direction at time 0. All right, now a key part of these problems is that you'll need to have some way to define the energy eigenvectors. And so here the problem says, let's suppose the energy of electrons that are in the state aligned with the z-axis positive, say that energy is E positive, and energy of electrons in the state negative z is energy negative. Now this would be the case, or a good example of this would be if there happened to be a magnetic field in the z direction. Then basically if our electrons that are either aligned or anti-aligned with that direction will have an energy associated with them. And so that's where the energy comes from. And so here that's given to you there. And so in this problem we were trying to find the time evolution of this state. So our steps, we're going to go through them again. So we're given the initial vector. Now here our initial vector at time 0 we're told is the positive y vector. So that would be sort of our initial vector at time 0. So the first step is to determine which eigenvectors are the energy eigenvectors. And so in our particular case, those would be the positive z and the negative z. All right. Now it took a little bit of reading here to do that, but we can get them from this little paragraph here. And so now the next step will be to write our state vector at time 0 in terms of these energy eigenvectors. And so we'll do that in a second. And then once you do that, you multiply each eigenvector by this new complex exponential time evolution term. And then, of course, once you do that, we can calculate the probabilities of various observables. So let's go ahead and just try this now. So here's the same problem, all right, and we did step one. So step one was to find the energy eigenvectors. There are these two guys right here. So step two is to write your vector, the positive y, in terms of these energy eigenvectors, and then time evolve it by multiplying by this complex exponential term. So give this a try, see which one of these options here, so these are 4 options for the state vector as a function of time. See which one makes sense to you, and then we'll talk about it, and hopefully we'll get to the same answer. Okay, so the answer I get is A, so hopefully you agree with that. But let's go through this kind of slowly and show why it's A. So first of all, we know that our initial state vector at time 0 we're told is the positive y vector. And this is the vector here. So they describe this and they actually show you how you can solve for this in the appendix of the text. Now, the thing is whenever your eigenvalues are the positive z and the negative z, all right, it's pretty fast to actually take this and expand it out. And basically what you can do is write it out just like this here. Okay, so whatever the piece is times here, well, we know that our positive z vector is 1, 0, and our negative z vector is 0, 1. And so basically here, times this first piece is going to be what you put over here. And so my factor times that 1 is 1 over radical 2, 1, 0. And then this other factor over here would be radical I over radical 2. And of course, if we just sort of expand this out a little bit, okay, so I'd have 1 over radical 2 here times 0 if I multiplied that in, and then I'd have 0 I over radical 2 there. And so I end up, coming out with the exactual vector that I want. So because these two things are very simple, you can actually say that basically the basis we're working in is the positive and negative z basis. But another way to sort of phrase that is because these vectors here are so simple, it's usually pretty quick to write this out in terms of the positive z and the negative z. And so technically with this, another way to write this would be 1 over radical 2 positive z plus I over radical 2 negative z. And so it's the same thing. We talked about this last time of sort of there's 2 ways to express your vector generally. You can express it as this column vector, and then in general you can express it as a linear combination of any of the sets of eigenvectors. And so we write it out this way here, and so this is our second step. We've written this in terms of the energy eigenvectors, all right, so we have something like this, and now the third step is just to put in that exponential piece. And so we just literally put in this exponential piece, e to the negative I, the energy we're talking about, times time divided by h bar. Okay, now this is kind of weird. Again, we're going to talk about this and justify it more, but for right now we're just trying to get an idea of how this works. So I multiply here. We're told that this state, the positive state, has an energy E positive, and this state here, the negative, has this energy E negative. So I write it like that, and then just sort of combining this up again, just like we sort of just did a second ago. So now I'm going to write this as a column vector. Okay, if I multiply these through, it comes out as a column vector like this right here, which is generally easier to use once we're making calculations. So make sure this all makes sense to you. So we've sort of done the first couple of steps here in our method. So make sure this makes sense before going on. So we're at the point now where we've solved for our time evolution of this system. So this is the time evolution of our state vector. So we've gone through, we've done that. We'll do that in other cases, but we want to stop now and just sort of try to interpret this. Because right now you look at this, it doesn't sort of mean much to you, probably. And so the first thing we want to do then is, so now we've done this, so suppose an electron is in this state here. So that's the time evolved state. Now what is the probability that this electron will exit from the positive channel if it is sent through an SGY device? All right, so give this one a try. And so this is the positive channel. And again, I'll give you the vector here. So this is 1 times radical 2 1i. So pause this here and then try to find the probability that will measure this electron in the state positive y. And then we'll talk about it here and see if we get the same answer. Okay, so I got this here. So let's go through this. And we're going to see that this turns out to be consistent with the spin precessing around the z-axis, which is what you would expect classically. Of course, you got to be careful. Consistent with doesn't mean doesn't tell us what the reality is, but still, we're going to talk about what that sort of means to us here as we go on. But let's calculate this and make sure that this makes sense to us, because there's always two parts to this. There's the calculating it, making sure you get the right answer, and then trying to understand what it means. Neither of them is terribly easy. So whenever we calculate a probability, right, we're always going to take an inner product. And so we're going to take the inner product of the bra of positive y and then this new state vector we calculated. So here's the bra of positive y. Be real careful. I changed that to a negative I because it's the complex conjugate. Now, I'm just going to slide this 1 over radical 2 out over here. So we basically have an out front factor of 1/2. And then here it's going to be 1 times this guy. So I get e to the negative I, e plus t divided by h bar, and then negative I times this. So I get negative I squared, e to the negative I, e negative t over h bar. So this is my complex number that I've calculated. And then, of course, here, negative I squared is just 1. So I can rewrite this a little bit nicer as just 1/2 this exponential plus this exponential. And so now, okay, to find the probability, so we've found the quantum amplitude. So to find the probability, we want to take the absolute square of this. And so I've multiplied, so this again is this is some complex number, right? This thing is some complex number. So down here, I'm going to take the complex conjugate of that complex number times itself. And so this is the complex conjugate. It's the same thing as over here, but with positive signs in here. And then here's just the actual number itself. And I pulled the two 1/2s out over to here. And so if we go through and do this, this is just for multiplying, so I'll call the different terms, like say A, B, C, D. And so to do this, if I multiply this term here is A times C. A times C, you got the positive of this thing, the negative of this thing, it cancels out to be 1. So that's really nice. This term here is my A times term C. So I got the positive I, E positive, and then, I'm sorry, it's the A times D term. So the positive IE plus and the negative IE negative gives me that piece right there. This piece is the B times C term. Okay, so my B times C term, I get positive e to the I negative, and then this is negative e to the positive. And so what I did is I pulled this negative out to make it sort of have the same shape as this one here. And you'll see in a second why I did that. And then finally, this is the term B times D, where again those two exactly cancel out to give us 1. And so if I go through then here, so what I'm going to do is make this substitution for omega that we hinted at in the beginning of the problem. All right, and so I get 1/4 1 plus, so this is just to clean these two pieces up. We can write them this way here. And of course, what we can do is add up the 1 and the 1, which gives me a 2, and then this little thing here is exactly equal to 2 cosine omega t. This is the kind of complex stuff we did in the first week of class. And so just clean this up a bit, and I get the 1/2 plus 1/2 cosine omega t. So once again, stop here and make sure you can calculate this and you follow how we did this. And we're going to talk now about what this means. So again, one hard part is calculating, one hard part is trying to interpret it. So he mentioned what should happen classically if you have a tiny magnet that's inside a magnetic field. And what it'll do is it'll precess around the magnetic field in a very similar way to what a gyroscope does. Now in our particular example, so what we're basically saying is that the magnetic field goes along the z direction, the z direction, and our initial direction of our spin is here in what we would call the y direction. And so what should happen is you should basically the spin, or I shouldn't say what should happen, but classically what you would expect is the spin to sort of precess around the z direction in the xy axis. And if you look at the probabilities of measuring positive z, positive x, negative x for this particular spin as its time evolved, it sort of does this. And so here's the actual calculation. So we just calculated the probability of it being positive y here, all right, over here. this guy. Now we can go through and do this for negative y too. I'll save you the details, but it's probably a good idea to go through and check that sometime. And so we get these two probabilities. And so if we look at time 0, so I've basically plotted out here 2 time evolutions of this. And so here's a little picture to kind of just sort of show you what's happening, or at least hopefully to try to make it a little bit better. And so here's the y direction, here's the x, and the z is coming out of the page sort of right at us. And then what should happen is our vector is starting out, our spin vector is starting out aligned in the positive y direction. That's our initial case, right? And if you look at the blue line, that's positive. So it starts at 1, and then as time evolves, comes down to 1/2. Now, when it's 1/2, one way to interpret that is that it's aligned with either the x or the negative x direction, okay? And then it comes down here to 0, and that would be that that vector is actually in the opposite direction. So if we kind of do this here, so initially it's aligned this way with our positive y. Now I don't know exactly which direction it's pointing in here, but aligned with the x or the negative x would put it sort of halfway in between positive y and negative y. So both of those results come out to be 1/2, and then down here you get 0, which means it's gone this way here. So that gives you a sense that this vector is rotating. All right, it's rotating either clockwise or counterclockwise, and so now it's pointed down. It comes back here again to being half likely to be spin up in the y, half likely to be spin down, and so it could again be sort of going this way or that way. Again, I'll sort of draw that picture over here to make that a little bit clearer. And then it comes up to here to finally being 100% likely to be spin up, and so you can imagine the vector is like this. And so if you sort of look at that, this vector then is in a sense rotating around, which again is the classical picture that we would expect at this point. All right, and finally, just to end, this is actually one of our pre-class questions for this assignment. And so we just I just went through and described how sort of the probability of positive y and negative y give you the sense that this thing is actually precessing around the z-axis. So this is, I think, really difficult to get, especially your first time through. Hopefully this helps. I would also read through the text. They do a very similar example. But here's the probability of this being either positive x or negative x. So again, I'll save you the details of calculating this. You can do it, but here's just the plots of that. So with these probabilities here, you can determine what the actual motion of this, again, what the motion seems to be. I say here what is consistent with this probability. So what motion is consistent with this probability? So give this a good look over and then answer this as best you can in the pre-class questions.